Hey guys, we are getting ready to do the absolute last section of chapter P, which means we are going to have a test on Friday, and I will talk more about that at the end of the notes. So we are doing exponential and logarithmic functions. You would have touched on these in Algebra 2, and you would have done a lot of them last year in pre-calculus. So properties of exponents are as follows. These are actually all taught in Algebra 1. So that would have been most of your guys' 8th grade or freshman year. And so just to review, a to the power of 0 is equal to 1. A being any positive real number. Okay, really that could work for anything though. Number 2 is if I have a product of things that have exponents and the base is the same, a being the base, I can rewrite that as a with the exponent of the exponents being added. So instead of a to the x times a to the y, I have a to the x plus y. So adding in the exponents is multiplication of the bases with exponents. This is the product, or this is the power to power rule. Number 3, a to the x to the y. That's an exponent to an exponent. You multiply those. This is a power of a product, which means they are being multiplied before the exponent happens, and they can each have that exponent. I hate to use the word distributed property. That's not the distributed property, but that's kind of what it looks like in our familiar setting of what we know before. All right. Same thing goes with division. If I have a to the x divided by a to the y, I can actually combine those like we did with multiplication, but in this case, I'm going to subtract. It is the top exponent minus the bottom exponent. Kind of picture like x cubed over x squared. If I were to write out 3x's and write out 2x's on bottom, the answer is going to have an exponent of those powers being subtracted because 2 of them are going to cancel out. That is why you subtract. This is power of a quotient. So each part of the quotient gets the power. And then power of a negative exponent, it moves it across the divide line. So if I had a negative in the denominator as an exponent, not the base, I can move it up. In this case, it shows a negative in the numerator. I can move it down. It can work both directions. Okay. All right, so we'll practice. So we're going to simplify. So if you notice, our bases are the same. We both have a base of 2, which means I can use, this is a product of powers. So I will give them the base, and the exponent gets to add. Okay, that was one of those from earlier. So this is the same as 2 to the 5th. If you're not sure, it's 2 times 2, which is 2. Hold on one second. My dog is crazy. Mickey, no. Okay. So if you have 2 2's and 3 2's, and how many total 2's do you have? You have 5. Okay, so that's how that works. Then we'll do this one. Well, again, that's a quotient, okay, of powers. And so with the same base, they have to have the same base. We'll have 2 minus 3. It's always the top minus the bottom. Okay, and whenever we do that, we will get to the negative 1. Don't leave negative exponents your final answer. We should fix that, so that'll use that last property we did. You can write it like that, or you can write it like that. All right, and then we have 3 to the x cubed. Okay, that's a power of a power rule, and those just go multiplied. And then the last one, each thing gets the power, so I will have 1 to the negative x over 3 to the negative x. And when I do that, then I can move that 1 with the x down below. It'll make it positive. And I move that 3 to the x up above, and it'll make that exponent positive. Okay. Something you could have also done was, from the beginning, you could have flipped that 1 over 3, and done it like this. And then you would have multiplied the exponents. You would have got the same answer. Okay. This does simplify. 1 to any power is just 1. I would take either of those answers, though. All right, so we are going to sketch these. And a good way to sketch these is to make an XY chart. So I'm going to make an XY chart for all 3 of these functions. And I'm just going to label them at the top. We have 2 to the x, and we have 1/2 to the x, and we have 3x. Okay, so I can see. Good suggestion on things to plug in. If you notice, there's no addition or subtraction. So these would be centered at 0, 0. So I'm going to do -2, -1, 0, 1, 2 for all of them. So once I have those set up, we will just fill them in and graph them. All right, so for f of x, we have -2 as our what we're plugging into. So we have 2 to the -2, which is 1 over 2 to the -2, or 2 to the 2, which is 1/4. Okay, does that make sense? And you don't have to write out this step there if you don't want to, but that's where that comes from, is that negative exponent would move it down below. So likewise, we would end up with just 1 over 2 here. Anything to the power of 0 is 1, 2, and then 2 squared is 4. And so then I can go and plot those points, and I would have -2 and 1/4, and I would have -1 and 1/2, and 0 and 1, 1 and 2. If you notice, it climbs very fast. That is a characteristic of these. It does not cross the x-axis unless it has been shifted. Okay, I'm going to change colors. Okay. All right, so then we have the next function. If I plug in -2, I will have 1/2 to the -2 power, which would again flip that. Okay, it's going to make it be 1 over 2 to the 2 power, which would be the same thing as 2 to the -1. So it's going to be 2 squared. So we will get 4. See if I can squeeze that in there. Okay, so same kind of thing here. We're going to get 2 to the 1, so we just get 2. Plug in 0, we get 1. Plug in 1, we get 1/2. And plug in 2, we get 1/4. So I'll go graph this guy. So at -2, I actually have 4. At -1, I have 2. At 0, I have 1, so they cross at that same place. At 1, I have 1/2, and then I have 1/4. And again, it does not cross that x-axis. It'll actually get infinitesimally close to that x-axis. Okay, so as it goes farther out, it gets closer and closer and closer and closer, but never actually touches it. All right, we'll do the same thing with -2. 3 to the -2 would be 1 over 3 squared. Oh, let me change colors. Let's do green. Hopefully you guys will be able to see that. Right. Okay. And that's 1/9, so a very tiny number. And then, so we'll have 1/3 for the next one. We'll have 1 for the next one. We will have 3 and 9. So if I go and graph those, I have -2. I'm just going to make it really close to the x-axis, as close as I can get it, because it can't actually cross it. And then -1, I have 1/3. So I'm just going to try to go slightly above that. 0, 1 crosses that same place. 1, 3. And 2, 9. Okay. Oop. That was 3, 9. When you do your graphs, try to make them go out farther. Don't just stop where your points go. If you notice that h function climbs a lot faster. Okay? So use your XY chart for that. They'll all have that similar shape, even if with reflections going on. Okay, so then next we are going to talk about properties of exponential functions. All right, so we have our domain and range is one thing we're going to talk about, and then we also are talking about our x-intercepts and whether they are one-to-one or not. Okay, and so for an exponential function, which is what we just graphed, so something that looks like this, whether it reflects or not, okay, whenever you have that, it will have a domain of -infinity to infinity, which means it goes as far left, forever right. But the range, it starts at 0 and goes up to infinity. Okay? Y-intercept does cross at 0, 1, which you saw them all crossing at the same place. It is one-to-one. It does pass the horizontal line test. Okay, so it would have an inverse existing. So then if we go to properties of natural logarithmic functions, okay, so g of x looking like natural log of x. This one was exponential. This is natural logarithmic. Okay. It has a different look. Okay, it will look more like this. Okay, look a little bit different. Asymptote being here, where the asymptote here is here. Okay, left off parenthesis. So the domain of this is 0 to infinity. Okay, it'll start at 0 if there's no addition or subtraction going on, but the range is constantly up and constantly down. So if you notice our domain and range is flipped, that's because these are inverses of each other. Okay. Y-intercept would be now on the y-axis. I mean, down at the y-axis, where the other one had an x-intercept, or y-intercept. This one has an x-intercept. Okay, and it is still 1-to-1. So again, it has an inverse. They're inverses of each other. So if you were to graph them, they would reflect across that line, y equals x, that we talked about in a previous lesson. Okay, so those are just properties. Again, we're going to do some more properties. These are things that will be helpful if you're looking through your homework assignments, working on your test. You may want these in front of you. Natural logarithmic function. It is natural log of x equals b, if and only if. Remember, that's what that means. E to the b equals x. Okay, so these are inverses of each other. You notice they're using the same values, and the difference is whether there's an e. Well, the log, natural log, is log with a base of e. Those are the same thing. Okay, and essentially what the log is saying is what exponent, natural log, what exponent of e, this is what this is saying, what exponent of e gives me x? The answer to that would be. Okay, so if you were to kind of look at that in some other forms, it's kind of here, the logarithmic form would be natural log of 1 equals 0. So what exponent of 1, okay, or what exponent of 0 gives me 1, what exponent of e gives me 1, the answer to that is 0. Okay, that's where that matches. This one says what exponent of e, okay, gives me e, what exponent of e gives me e, well, that would be 1. And so these go across from each other because they are related to each other. Okay, natural log of e to -1 is just -1. Again, they're inverses of each other, so I kind of think of it like canceling. This cancels and it leaves me with -1. Okay, this is that same property we used before, though, where it goes down below. All right, natural log of e to the x is just x. E to the natural log of x is just x. All right, other properties, these are for when you're condensing or expanding. If it says to expand, your goal is to get things being added, subtracted, stretching it out like this. If it says to condense, you're looking for putting it as multiplication, division. Okay, so if I have multiplication within one log, I can rewrite it as addition. If I have division within one log, I can write a subtraction. Okay, and if I have an exponent, this exponent can multiply in front because it means it's happening added that many times. And so that number will just go down in front. Okay, if you have division and something expanded, it does not just magically get to become addition. It's got to be within one log. All right, so an example. So we have division going on. Division will be subtraction if you look back up here. So I will just rewrite that, and that's within one log. Natural log of the top minus natural log of the bottom. Oop. Okay. This one, I would rewrite it first, working my way outside of the function inside. So this exponent, well, that root is the same thing as an exponent of 1/2. A cube root is an exponent of 1/3. A fourth root is the exponent of 1/4. Those are things to remember. And so then I can take that exponent and move it down in front. And there's no multiplication going on in here. I mean, I know there's a 3 times an x, but there's an addition in there breaking it up. It has to be all products whenever you're doing that. So this would be my final answer for that. This one, though, there is multiplication, division, no addition or subtraction going on within that. So I will have natural log of the top minus natural log of the bottom, but this is multiplication within itself. So I would actually have to break that up into individuals if I was truly expanding this all the way. So what you're dividing, what's on the bottom is what's subtracted. The tops are being added. So then the big guy. All right, so we're going to break it down. So first I'm going to pull out the exponents. And I'm going to minus here because I'm dividing. And then I have natural log. I'm just going to rewrite this whole thing with its new exponent so that I can keep track of where I'm at. All right, so the top is done. There's nothing more I can do with the top, but the bottom does work out a little more. So I'm just going to rewrite the top. And if you notice, I have multiplication within my subtraction. So that would be addition within this. Okay, but the whole thing is being subtracted, so it too will be subtracted. If you notice that x is in the denominator, I am dividing by both x and the cube root of this. Okay, they're both being divided. So I will subtract natural log of x, and I will subtract 1/3 natural log of x squared plus 1. Since there's addition going on in here and in here, I can't break those down any farther. So then this would be my full expansion. You should be able to reverse these two. So if I give you the addition and subtraction one, like the circled things, I should be able to rewrite them as what they originally were. You'll see some of that in your homework assignment. Last two examples. Okay, our goal is to get x by itself, so solve for x. So we're going to use the fact that exponential functions and logarithmic functions are inverses of each other. So just like if I want to get rid of something that's added, I subtract. Well, if I want to get rid of something that has a base of e and is an exponent, I'm going to use the log. And vice versa, if I have something that has a natural log, I'm going to use something with the base of e. And that works too for any base. They just have to be the same base. So this e is the problem. It's trapping that x plus 1 in its exponent. So I need to get rid of the e. So what I can do is I can actually rewrite this function and take the natural log of both sides. Because using our properties, this left side is still natural log of 7. That's a decimal. But that other side, natural log of e to the x plus 1, it's just x plus 1, okay? And so then I can subtract 1 from both sides, and x is equal to natural log of 7 minus 1, which is approximately 0.94591. Okay, go out to 5 decimal places. The AP test will expect that of you. So we'll train ourselves to do that. So like our x was trapped in A, our x is trapped inside the natural log. I can't just get it out. It's not being multiplied. It's not being divided. Natural logs and logs are never empty, kind of like our sine and cosines are never empty. So I have to get rid of that. So what I can do is rewrite that as e to the exponent of natural log of 2x minus 3. What I do to one side, I do have to do the other. So I'll do e to the 5th power. Okay. And what that does is e to the natural log of anything is just that thing. So I'll have 2x minus 3 equals e to the 5th power. I'll add 3 to both sides, and I'll divide by 2. And I'll type that in my calculator, because e is a number. It's about 2.7 something. And I will get approximately 75.70658. Okay, so you will have a test on Friday. And your homework is also due on Friday. To review for this test, I would redo homework problems and make sure you have organized notes, because it is open notes. I will model the problems I'll expect you to do off of some of the homework problems. They won't be the same, but they'll have different numbers, different situations. But make sure you have that. You will have to take it between the times of 8 a.m. and noon. And since that's the case, you need to make sure you get it done that time. I don't care how long you spend on it. I just need you to get it done. Okay, this is our first experience test. So you're going to take it in Google Forms. Your answers, you'll type them in, or there'll be multiple choice, something along those lines. However, you have to attach a picture of your work, numbered. And on that crying baby note, we are officially done.